and really, again, thank you for turning up here. I know we have serious competition, but I'm pretty sure Satinder's talk is going to be as exciting as the match, if not.
No. Let's lower expectations. Let's lower expectations.
And if you remember, Sridhar put up this slide about the three famous alumni of the ALL, the Autonomous Learning Lab. So we heard one earlier, and here's the other one. And the third one was Michael Jordan. You're not getting it.
Michael Jordan. Right. That's right. Thank you. Thank you all for coming. Thank you, Ravi, for inviting me. And again, yes, I know if you want to listen to the score, please do. So I'm going to talk about a topic that I've been working on for a little while, called which we known by various names, called predictive state representations, sometimes called observable operator models. Actually, in fact, that's the way it was called earlier. And then spectral learning is more recent incarnation. I'm going to start with introduction to PSRs, predictive state representations, and then move on to a bit to the more recent work on spectral learning. So I don't have a sense of your background, so I don't know. You've all been here at least listening to the previous talks, is that right? Okay, so I don't need to introduce reinforcement learning. I don't need to introduce all of those things. So that's good. So I can, let's make this interactive. You're here. You may as well engage your minds. So ask me anything you like. Stop me. I'm happy to use the board. Things of that sort. So let's make it as interactive as possible. So what I'm going to describe is work done with a whole bunch of former students and current students and postdocs. But it started way back at AT&T with joint work with Rich Sutton and Michael Littman is where we started doing this work. And so I acknowledge Rich and Michael for much of the starting point of all this. And then, of course, it also goes back to someone named Herbert Yeager, who did the observable operator model. So this is just paying the dues to people who've helped build this out. Okay, so here's some motivation. So I'm sure I haven't had the luxury of attending the previous talks. I don't know what all has been said, but I can imagine at least what Rich would have said. What does it mean for an agent to know its environment? That's what we're going to talk about today. Indeed, for what does it mean for an agent to be intelligent? There are at least one way of carving up what it means for an agent to be intelligent is to use the following two terms, knowledge and search. Right? Agent has to have knowledge and then use its knowledge to do internal search, cognitive search, to be able to act in the world. And so you probably have heard a lot. So we're going to talk about knowledge and search. And my guess is you've heard a lot about algorithms that essentially do that search using knowledge. So at least for this morning, we're going to talk about knowledge and representation of knowledge. And that's what this talk is going to be about. So let's see. So what I'm going to mean when I use the word knowledge here for today, for this morning, I'm going to mean the ability to predict stochastically the action conditional future. So let me unpack that term, that phrase. So the ability to know when an agent does a sequence of actions or follows a policy or behaves in some way, what it's likely to happen. So predicting the future. And no, I cannot predict the future. I don't know what's going to happen in the match today. I don't have that knowledge. But so we're going to think about that ability to predict the future based on what actions or behavior the agent does. And so the question we're going to ask and answer is, how should it represent this knowledge about its environment? And of course, there are many, many different knowledge representations that many different communities have come up with, right? In science, across science and engineering. Differential equations, difference equations, linear models, finite automata, strips models from AI, Markov chains, MDPs, all of these sorts of things are different communities' ways of representing knowledge, capturing knowledge. Building a model is another way to think about it. And I'm going to often use the phrase building a model. And yet, of course, I think we don't really still have a clean handle or a great handle on how to build knowledge of models for complex AI agents in rich environments. So it's still an open question. There's still a lot to be done to build an ability to just put an agent in an environment and let it acquire knowledge and represent knowledge and learn knowledge and use it to many of these pieces we know, but knowledge representation still remains an interesting challenge for AI and for agents in general. Okay, so I'm going to walk through a particular way of modeling, which has the property that the knowledge learned, well, it's a learnable representation, learnable knowledge, it's verifiable. And I'll talk about all of these things as I go along. It's maintainable. It's a kind of knowledge that the agent can learn and maintain and correct as it experiences the world. Verify its knowledge and therefore maintain it. And then, of course, it should be plannable. That is, the agent should be able to take that knowledge and compute how to behave in the world. So planning is important as well. Okay, so I'm going to focus on predictive state representations, again, which came out how many years ago? 13, 15 years ago from AT&T. And then I'm going to give you an introduction, and then I'm going to dive into some new results. Okay, so I didn't realize there were all these animations in this talk. So I'm going to describe what PSRs, or predictive state representations, are and relate them formally to what are called partially observable Markov decision processes. Has POMDBs been talked about at all? Not really? Okay. So I'll describe some POMDB stuff in a bit, and then I'll go to the rest of the talk. Okay. So here's a view of a uncontrolled dynamical system. So an uncontrolled dynamical system is a dynamical system in which there are no actions. It just emits a sequence of observations. So maybe you're passively listening to someone speak. So you're getting a sequence of symbols. Any situation where the agent is simply receiving a sequence of observations without acting in the world could be thought of as an uncontrolled dynamical system. It's a special case of a controlled dynamical system, which we'll get to in a minute. So an uncontrolled dynamical system produces a sequence of observations. So that's superscripts denote time. So it just produces a sequence of observations, O1, O2, O3, okay. So it just emits a sequence of symbols. That's what an arbitrary uncontrolled dynamical system. Let's assume, for the rest of this talk, I'm really going to, for ease of exposition, assume that the symbols are discrete, finite in number. So an arbitrary uncontrolled dynamical system is really just an emitter of a sequence of symbols. Like today, I'm an emitter of a sequence of characters that you're hearing. Okay. And so speech is an example, stock market predictions could be an example, weather could be an example, and so on. Okay, here is a view that you've seen, I'm sure. You have an agent interacting in the environment. So this is a controlled dynamical system. And so now here, we're going to talk about sequences of actions followed by observations. Actions, observation, action, observation. Okay, so control AI or robotics. You've all seen what an MDP is. I just want to distinguish between the Markov assumption and not making the Markov assumption. So an observation model in general is and here's what I'm beginning to use the word model, and I hope you've heard the word model as it's used in reinforcement learning. So it's the ability to predict future observations and future rewards. We won't do much with rewards today. I'll do mostly about observations. So the observation model would be the conditional probability of the observation at time t+1 given the entire history of observations and actions. So this is written in reverse order: beginning of time, current time, next time. Okay? So if you can make the Markov assumption, which is what, when you make a Markov decision process, MDP, if you can make the Markov assumption, that assumption says the conditional distribution of the observation at time t+1 given the last observation action is the same as the conditional distribution over the next observation given the entire history. So that's the Markov assumption. And the same thing for reward. When you have the Markov assumption, you get an MDP, you get these nice transition probabilities. So this is the probability when you take action A in observation O, what is the probability of seeing an observation O prime. time goes away under the assumption of stationarity. So this is a stationary Markov decision process. Okay. So today we're not going to make this assumption. This morning we're not going to make this assumption. So we won't be able to assume that you can ignore the history. Okay. So it's all about, this morning's lecture is all about when you can't ignore the history. Okay. And when the general problem, when you can't ignore history, is called a partially observable Markov decision process. Okay? All right. So again, for today, I'm going to talk about discrete time, finite observations, and I'm going to talk about both controlled and uncontrolled dynamical systems. I'm going to start with controlled, then I'll switch to uncontrolled at some point. Okay, so what does it mean to predict the future? Predict the future, in this case, in an uncontrolled dynamical system, I'm going to use the word the test T to mean a future. And in a controlled system, a future is a sequence of observations for a sequence of actions. So test is A1, O1, A2, O2, AK, OK. So prediction for a future in an uncontrolled system is just a probability of seeing that future. So the prediction for a test, P of T, is just a probability that you see that test. So you could have tried to make a prediction of what I might say in the morning, and the probability of hearing that would be your prediction of that particular sequence, right? So the prediction of a test T is the probability that you see exactly that corresponding sequence O1, OK at time 1 to time k.
You just changed notation on us there.
No, subscripts denote time. Superscripts are just an arbitrary sequence. So the test is some arbitrary sequence of observations. The prediction of a test is the probability that you see that arbitrary sequence of observations, say a length k sequence, in the first k time steps. Thank you for asking me to clarify. Is the notation clear? Because the notation isn't clear, the rest of the talk will get a little bit hard to follow. Right? So subscripts here denote time. Superscripts are just elements in a sequence that I might be trying to make a prediction for. Okay, in a control system, the prediction for a test is the probability of seeing the corresponding sequence of observations in the test, given that the agent takes the actions in that test. Now, there are various ways to get really picky about this, but don't worry about that. Just think of it as, if the agent were to behave according to the action sequence in the test, what's the probability that the agent would see the observations in that test? If you can make these predictions, well, I'll come to that. So a system is a distribution over all futures, so all tests. So here's a exhaustive, enumerative definition of a system. An arbitrary dynamical system can be viewed as exhaustively represented, if you like, or conceived of as a set of numbers, right? Where I'm going to extend this into a matrix in a minute. Right now it's a vector. So this is first test, second test, third test, fourth test. What are these tests? All length 1 observations, all length observation actions, all length 2 observation actions, all length 3. So different length futures. I've just laid them out in an infinite vector. So what's the probability that, so let's imagine a very simple alphabet, the English alphabet, A to Z. So the first, how many letters in an English alphabet? 26. I was trying to think that. So the first 26 of these entries will be the probability of seeing an A as the first symbol, probability of seeing a B in the uncontrolled setting, probability of B as the second, as the first symbol, probability of C as the first symbol, D as the first symbol, and so on. And then after that, after the first 26, it'll be probability of seeing AA as the first 2 symbols, AB, and so on. Every pair, and then every triple, every 4 tuple, and so on. So you can lay out these numbers in an infinite vector, and it fully specifies the system. Obviously, this is not a representation you would keep. I'm just helping you conceptualize the system, and then I'll show you a representation that an agent could actually use. Okay? So this is just a infinite representation that's explicitly laying out the probability of every possible future. And each of these numbers in the vector is a probability. The probability of this length future, of this specific future, right? Probability of this specific future. So if you have all these numbers, then you've got the system. You've got a description of the system. Is this making sense? Okay. Now, of course, again, this is not a useful representation because first of all, it's an infinite vector, and we haven't really talked about how to build up this vector and so on. But I'm just saying every dynamical system has a corresponding, I think we're going to call it system dynamics vector. Yeah, it's called there. System dynamics vector. So every dynamical system has a corresponding system dynamics vector representation. Okay, good. Now there are lots of constraints in here, right? Because, well, first of all, there may be zeros in here. Some features may not be possible. Then lots of things have to sum to 1, right? So in the English alphabet setting, the probability of seeing the first letter being an A to Z is 1. So those numbers have to sum to 1. All doubles have to sum to 1. All kinds of conditional probability rules have to be satisfied. So there's lots and lots of constraints here. You can't put arbitrary numbers in here. Right? It has to satisfy all the rules of probability and conditional probabilities and all of that. Okay? So it's not an arbitrary. You can't just make an arbitrary put numbers here and say, well, that's my system. It has to satisfy the rules of probability. Okay. All right. So the point that would be important here is that any exact model of a dynamical system should be able to generate this vector. Should be able to compute this vector in principle, right? Because that's what the system really is. I mean, in the abstraction being used here. Okay, so now let me extend that vector, which is now the first row of this matrix, and extend it into an infinite matrix. It was an infinite vector. Now I'm going to make it an infinity by infinity matrix, which we're going to call a system dynamics matrix. And why I'm doing this will be clear in a few minutes, I hope. So now we're going to think of the columns as futures or tests, and the rows as histories. So the first row is from the beginning of time, the null history. So the symbol phi here is for the null history, for the empty history. And so all length 1 histories, all length 2 histories, all length 3 histories, all length 1 test, all length 2 tests, all length 3 tests, and so on. Now, of course, the first row itself contains all the information there is that captures the system perfectly. So all of this is redundant information. So what's the entry here in the matrix? So the jth row, for the history corresponding, history H sub j and test T sub I, the number here can be thought of in 2 ways, but I'm going to do it the way I've written here, which is the conditional probability of seeing that future given that history. So now it's history conditional futures. Okay, so again, this is very abstract. Every dynamical system will have a corresponding system dynamics matrix. Okay? But again, you should be thinking, why is he telling us this? What is he going to do with this? And I'm about to get to what I'm going to do with it. So at least, but if you have questions about what this representation is, please, or this abstraction is, do ask. Yes, please.
So each one of those TIs is a vector of observations and actions.
Each TI and each HJ is a sequence of alternating actions observations. Yes.
I see. And that's an infinite sequence in itself?
No, because remember, T1 to some TK are length 1 futures. Then after that, all the length 2 futures. So if it's a finite alphabet, finite symbol set, then the number of length 1 is finite, number of length 2 is finite. So it's an infinity by infinity matrix, but this is a very specific length future, and this is a very specific and specific length history. So this is the conditional probability, and I think I have that. Let me just, right. So let me put both of these. So imagine a test of length k, history of length n, right? So let HJ be some very specific history of length n. So subscripted by time because this has happened. Some possible future, superscripted, some arbitrary sequence of observations. In the unconditional setting is the conditional probability that from this point onwards, n plus 1 to n plus k, the observations received are exactly this, but conditioned on the history. And in the control system, when you have actions and observations, it'll be if this has been the history of the agent so far, and after this it takes the corresponding actions in here, the action subsequence, what is the conditional probability of seeing the corresponding observations? Okay, so it's a number, right? It'll be just a number in here between 0 and 1. All of these numbers are between 0 and 1. Yeah, stare at this for a minute. If you don't get this, the rest of the talk will not be much fun, or, well, I don't know about fun anyway. Yes.
Before you said that just the first vector, first row is enough to
Yes.
characterize the system, but now you're saying all the remaining rows are also important.
Well, I'm going to do something with this idea, this abstraction in a minute. It's a matrix. Let me anticipate where I'm going to go. I'm going to talk about the rank of this matrix, and then I'm going to do something with the rank of that matrix. But you're very right. The first row is all the information. So let's ask, how would we compute this number from the first row? So this number is the ratio of the probability of the sequence Hj followed by Ti, which is somewhere in the first row, divided by the probability of just H sub j, which is also somewhere in the first row. So this entry is the ratio of two numbers in the first row, right? It's the probability of the concatenation of Hj followed by Ti, of that longer history or longer sequence, divided by just the probability of H sub j. Right? So each of these numbers can be generated from the numbers in the first row. So the numbers in the first row were enough to beat a dynamical system. I'm just making it into a matrix because then I'm going to do some matrix algebra with it. Thank you for asking questions. Please do ask, because otherwise,
Excuse me.
what's the point? Yes.
So in the control system case, you're actually putting the actions also in the conditioning, right?
Yes. So there was some history that's already been experienced. So this is a possible future. So the question being asked, that's being answered in this conditional probability, is after this history, if you take the subsequence of actions in this future, what's the probability, conditional probability, that you see the corresponding subsequence of observations from that point onwards, from this history onwards? Yes.
Why do the sequences start with an action in the control case? Don't you see some initial observation and base your first action on that? Like,
Let's imagine the first observation is what it's the empty symbol, if you like. You can do all this with the other way around too, but the notation is written this way. Good. I can see why you might think you'll first see something and then you'll act. That's fine.
Can there be repetition in the sequence?
Sure. Many of the actions might be the same. Many of the observations might be the same. It's, the history is whatever just has happened so far, right? So it could be that you took the action north. You saw, imagine a grid world. I don't know if you saw any grid worlds, but imagine that you took the action north and you saw some observation, some sensor reading. Then you took again the action north, and maybe you saw the same sensor reading. It's possible. So it's just, think of these just O's as belonging to some set of observations, and the actions as belonging to some set of actions. And these are arbitrary sequences of A's and O's from those sets. Right? So to capture a dynamical system or every dynamical system has a corresponding system dynamics matrix. Because every dynamical system will generate sequences or action conditional sequences when it's when it's an action-based system, and therefore you'll get these numbers. Notice there's no assumption of stationarity. The only assumptions being made are discrete observation, discrete action, finite here, and discrete time, because I'm talking about the first time step, second time step, third time step. But I'm not making assumptions about notions of stationarity or anything of that sort yet. Right? Just an arbitrary discrete time finite observation action system has a corresponding system dynamics matrix. Somebody had the hand up there. Yes.
I mean, even the first vector has redundancy, right? I mean, the two symbols, you can do a summation and get the marginal.
Absolutely.
The first symbol.
Absolutely. All the laws of probability hold. So marginalization, conditioning, all of those things also hold. Yes, absolutely. So there are many constraints, not unconstrained. You can't put arbitrary, even the first, everything below the first row is defined by the first row, right? But even the first row is not an arbitrary, you can't just put arbitrary numbers between 0 and 1. They have to satisfy the laws of probability. The one of them you just said, that when I marginalize out things, the appropriate number has to be there. Exactly right. Okay, so let me get you to at least some fruit to this soon. So, okay. Right, so all rows are determined uniquely by the first row. So now, this is a matrix. This matrix has a rank. It could be infinite, but it has a rank. So I'm going to use the phrase linear dimension to mean that rank. And let's say the system's rank is n for now. Now I'm only going to talk about finite rank systems, not talk about infinite rank systems. And you might be thinking, well, finite rank systems surely can't be very interesting. And I'll show you that finite rank systems are indeed quite interesting. Okay. All right. Okay, so any model must be able to generate this matrix. Okay, so let's see, I hope this is a slide. Yeah. So now imagine that the system has rank n, and let's imagine that I'm just going to shuffle the columns so that the columns between these red lines are n linearly independent columns. So what does it mean for a system rank to be n, matrix rank to be n? It means that at most, not unique, but at most n linearly independent columns, and similarly n linearly independent rows. Right? That's what a matrix, that's what a rank of a matrix is. Okay, so let's imagine these are the columns that are a set of columns that are linearly independent. Again, they don't have to be unique, of course. Okay, so now let's label these columns specially, Q1 to Qn. Okay, so here's the interesting claim already. In any history age, if I give you these n numbers, I have captured all the information there is in that history, because I can compute the prediction for any future. I can finish this row just from these n numbers. By the fact that every column is a weighted combination of these n columns means that I have to know the weights, which I'll tell you about in a minute. But every number here, all the extension, infinite extension, and earlier, are all computable from just these n numbers. Right? Just for the fact that this is rank. Okay, so now let me stop and make sure you get the importance of this. So these n numbers are a sufficient statistic of history in that any prediction of the future, any prediction about the future from that history can be made just from those n numbers. So notice this history could be very long. This age could be 1 million long, could be 1 trillion long. It'd still be these n numbers. By definition, that this is the rank of this matrix. Right? Just by the fact that this is the rank of the matrix, the rank of the matrix is n, and these are n linearly independent columns, all I need is these n numbers, and I've got I've captured all the information there is in the history. In a slightly more formal language, it's a sufficient statistic for predicting any, is a sufficient statistic of history for predicting anything in the future from that history. Yes, Rich?
By constructing it, you mean there's some weighted combination of those things?
It means that this has all the information there is in the history. So any prediction you could make from this history, I could throw this history away, and you could make from these numbers, these n numbers. But of course, as Rich is trying to get at, to make the prediction of some test here, I'll need to know what particular weights that combine these columns that produce that column. I'll talk about that in a minute. Okay, everybody with me so far? All right. So I can make a prediction. I can compute a number. Okay, so that means for every test t, every future t, every test, there will be some combination m sub t, so that I'm writing it as an inner product. When I want to make the prediction for this test, this future, from this history h, I take these n numbers in vector form. This is the probability, this is the vector notation of Q, the set of, I'm going to use the phrase core tests. So I'm going to call these core tests. So it's that n-dimensional vector, inner product with the weight vector, m sub t, that's going to produce this number. And m sub t will be a function of t, right? This m sub, the weight vector, if you like, will depend on which future I'm trying to make a prediction for. Yes?
So it looks like if you have a Markov process, then all the rows become dependent, right? So it's
I'm
rank
going to
one.
relate this to Markov chains and POMDPs in just a few minutes. Okay. I'm about to do that. I want to make sure everybody gets this first, then I'll move on to exactly that. Yes? Maybe I'm going too slow.
MT
M sub t. Is it?
doesn't depend on age.
That's the crucial thing. Thank you, Rich. So it doesn't depend on age, and that's the whole point. That's the whole point. That the weight vector here, m sub t, to produce this column, the same weights, this column is a weighted combination of this, independent of the row. That's the whole point. The entire advantage or entire reasoning here is that m sub t is not a function of h at all. Good. Thank you, Rich. Okay. So prediction for any test is a linear combination of predictions of the core test. Okay. So now let's go to your question. So suppose you have a Markov model. Let's make it a little bit more general. Let's imagine you have an nth order Markov model. So what's an nth order Markov model? An nth order Markov model is a model in which the next observation's probability only depends on the last n observation action pairs. So remember going back to the slide where I had this arbitrary history dependence? If you can cut it off, if you can say that the prediction for the next observation is only going to be a function of the last n observation actions, not all the way back in time, then it's an nth order Markov model. So the point is that suppose that, I'm based on the length, the number of observations, the number of actions, if the number of n-length histories is some k, because suppose there are 2 actions and 2 observations, then you'll be powers of 2. Okay. Then at most there will be k unique rows, right? Because any 2 rows with the same suffix of length n will have the same predictions, because it's an nth order Markov model. So a nth order Markov model, or a sort of let's call it k. Right. So and let's imagine that the first k histories are the unique are histories that are unique, and everything else is the same histories. Well, then what's the maximal rank of this system? If there are at most k unique histories, the maximum rank is k. Right. So here's an example where a nth order Markov model will have a finite rank. So at least it covers nth order Markov model. And I'm going to show you it covers POMDPs in a minute. Okay, that's where I'm about to go to. Okay, so it's a trivial theorem, all k history in the sense of the number of possible n-length histories is k. All k history Markov model are dynamical systems of linear dimension at most k, by just trivial proof. If the number of unique rows is k, well, the rank can't be more than k. Okay. Okay, so now let me do the opposite theorem. There exist dynamical systems of linear dimension n that cannot be modeled by any finite order Markov model. Okay, so you know what, I'm going to prove a more general statement. This will be a special case. So let me not do that. Let me just do palm DPs. So here's now a different abstraction. How many of you have seen something like this before? Okay, not many. So let me explain this to you. So this is a very nice graphical form for what's called a partially observable Markov decision process. So here in this row are states. First is time, t plus 1, t plus 2. These are subscripts at time. And each node here represents the state. So state at time t plus 1, t plus 2. Upper row is actions. So the state at time t plus 1 is a function of the previous state and the action taken. And each state generates observations. So now I'm trying to think about and connect this to things you might have heard of in this workshop. So okay, so when thinking about dynamical systems, probably the most standard way of thinking about it is to say, look, there's some reality out there. I can't see it. All I can see is through sensors. But it's some true state. I can't see it. All I can see is observations, O's. But the observations are generated from some true state of the system. And so this is the temporal evolution of the true state of the system, which is now going to generate observations. So I just get to see the O's, and I get to take the actions. I don't get to see the S's. So partially observable Markov decision process model is where you assume that there's a true state in the underlying world called nominal states sometimes, or hidden states. You get to see observations, and the actions influence the state, and this is might be called a graphical model form of a POM-DP, partially observable Markov decision process, and it captures all kinds of nice things like saying that given the state, this observation is conditionally independent of this state, because this state produces this observation. So if that's what's meaningful to you, hopefully it helped. Okay, so somebody wants to ask, does anybody want to ask me a question that will help you understand POM-DPs better? Yes?
Why isn't the action dependent on the state? So as an agent dependent on the state?
Action could be dependent on the state, but that's an agent choice, right? That is you could learn a policy where the action choice, the optimal action choice, could be dependent on the state. But the reality is the action is an exogenous input in this system, right? That is, I could take any action, divorced from what the previous state was, and I would get a next state, right? The fact that you think about actions as being a function of a state is because you're thinking reinforcement learning, you're thinking, I'm going to learn a policy, my policy's choice of action is going to depend on the state. But the action is just another input. It's just an external input into the dynamical system. If you think of a dynamical system, right, the actions are external inputs into the dynamical system. And yes, to control the dynamical system, I might choose the action depending on the state, but that's a different thing. Okay, so, but this is kind of important to get. But I'm about to show the following. Let me just make sure. Let me anticipate the result I'm about to show, and see if you guys will get it. I'm about to show that any POM-DP with n underlying hidden states, can be represented by any POM-DP with n underlying hidden states. The corresponding system dynamics matrix will have rank at most n. So that's what I'm about to show. Okay, so this should be puzzling and surprising, perhaps, if you're getting this. So I want to pause and make sure you get it. So a POM-DP can capture information that's arbitrarily far back in the past. So a POM-DP is much more powerful than an nth order Markov process, Markov model. Because through these hidden states, it can capture information that's arbitrarily far back in the history, in the past. So for example, you wake up in the morning, you put your key in your pocket, and you don't just have to keep checking all the time that you have your key in the pocket. So something that happens at the beginning of the day somehow influences your action choices for the rest of the day. So no end thought of, and suppose you can't observe the fact that you have a key in your pocket, you can't feel it. So that observation is not available to you, but somehow something that happened way back in time, at the beginning of the day, allows you to influence the actions throughout the rest of the day. Palm DPs can capture that, because you can imagine that there is some notion of state of the world, the reality of the world, in which the key is in my pocket, and you can sort of somehow maintain a distribution, maintain a belief that your key is in your pocket. Maybe we're just literally remembering that. But otherwise, there's PalmDB gives you more machinery that allows you to sort of keep that, and then so it's much more powerful than any finite history model. Any model that can only use observations that were obtained in the last, say, k steps or n steps. Is that making sense? Yes.
So my doubt is, since you are observing only a part of the state, that's why you are, in a MDP sort of scenario, you would be observing the whole state as such.
Yes, so in MDP, this would be exactly that.
Right.
That would make it an MDP.
So
because this is not that,
that's why you are able
PalmDB.
to capture the whole of the history, because there is something extra in a state which is not there in observation.
That's right. So just this observation is not enough to capture what's in the history, right? History of observations. So how PalmDBs work is that they take this history of observations and they maintain what's called a belief state. They say, okay, given the history of observations, I maintain an internal subjective distribution, if you like, belief state distribution, or possible states of the world, right? And so the representation there is that of a belief state. Now, if there are n possible underlying states, the belief state is an n-dimensional probability vector. Belief state is an n-dimensional probability vector. Is what are the possible states of the world? So imagine, let's make it more concrete. Imagine you have a grid world, but you don't get to sense the grid location you're in. Instead, all you can sense is are the neighboring squares occupied or not? So you have some bump sensors. Maybe it showed you a video of bump sensors. So there's a bump sensor up ahead, north, south, east, west. Let's imagine you have bump sensors. So you can tell if there is something bumping into you, north, south, east, west. You have a pen? Yeah, there's a pen. Okay, so so the belief state representation, so let's imagine we have it's not a permanent marker, is it? Okay, so imagine you have a very simple grid world. And maybe there's some obstacles. And you have a bump sensor. So you know that there is an obstacle here, you know this is free, you know there's an obstacle here, and this is free. So the observation is simply that north is blocked, east is free, south is blocked, west is free, right? So that's your observation. The true state is, let's call these states 1, 2, 3, 4, 5, 6, 7, 8, 9. The true state is 8. So state 8 generates the observation, north is occupied, south is occupied, east is free, west is free. Okay? So that's the observation. So now imagine you get a sequence of observations. So let's imagine the robot goes like this. It gets a sequence of observations. So all it has is a sequence of observations. It doesn't know exactly where it is. But maybe, if you had a model of the world, then you could maintain a distribution or possible states you could be in. So for example, well, this is not a great example because this may be the only state in which you get, no, this state, right? So for example, state 8 and state 2 are what's called aliased. So all you know is that this is your first observation, then your belief would be you're either here or there. And typically these problems you start with some initial distribution over possible states. So you might have some initial distribution of starting states, and if you see this observation, so let's imagine this probability of starting here was 0.1 and 0.3 here and the rest was elsewhere. So then after seeing this state, this observation, you'll have 0.1 divided by 0.4 probability of being here and 0.3 divided by 0.4 probability of being Okay, so I'm just giving you a little introduction to PalmDBs. And so now if you move here, right, you will now have blocked here, right, and free here and free here. And then you will get one more observation, and then you will update your distribution. So this is a PalmDB with 9 underlying nominal states and 2 to the 4 observations, because there are 4 bump sensors and they can be free or occupied. So the observation you will get is the sensor readings, and the true state is the true state of the system. So that's a PalmDB. And just like all the algorithms Rich talked about and other people talked about of doing TD and Q learning, there are extensions of those algorithms or how to apply those algorithms to PalmDBs and other algorithms too. Any questions about PalmDBs? So what I'm about to show, so this is probably the most conventional, traditional way of thinking about dynamical systems when you are not in the Markov setting. So this is sort of the competing model, if you like. Yes?
So in the PalmDB setting, as opposed to the conventional MDP, one is not only sometimes maybe interested in the rewards, but in a way you might have to take actions or policies that sort of give more information about so that the belief is getting updated in a better way. So there is a trade-off between.
Yes. So taking actions in the world have 2 consequences. Well, they always have had 2 consequences. They change the state of the world and they give you a reward. But now, the state of the world is a state of knowledge about the world, right? With just this one observation, the state of knowledge was, well, with some probability you're here, some probability you're there, right? And so actions will have, again, as an MDPs, have a consequence of giving you a reward, but also updating your knowledge about the world. So it's not just which physical state you're in, which is also true. So 3 things in this case. It changes the physical state you're in, which you don't get to see, but it changes your knowledge about the world, your representation and belief state of the world, anyway, in this case. I'm a little trouble calling it knowledge about the world, but anyway, yeah.
So,
Yes.
taking this question forward, can we think like in PalmDB setting, you take action for exploring the whole environment also, just instead of looking towards reward?
Okay, so all these are great questions. Well, let me at least answer this one. I'm not really going to talk about control yet. I think both of you are trying to ask the question, is it interesting in PalmDBs to take actions to calibrate, to know which state you're in? In certain settings, you can imagine that would be the optimal way to behave, right? But it's not a goal in itself. The goal in itself is to obtain reward. It may be that in obtaining reward, the optimal policy has a aspect to it that you can look at and say, oh, it's doing those actions because it's getting more certainty about which state it's in. But that's just a interpretation of what it's doing, right? The goal doesn't change. The goal is the RL goal of acting in the world so as to optimize some measure of cumulative reward. So that doesn't change. But the behavior might have the property that you're both sort of getting at, which is that it might be that the optimal way to behave might be to first sort of, push some buttons to sort of see where you exactly are and then take an action. That should fall out of the optimal policy. It's not an end in itself to seek information about the state. Okay? All right. So I'm going way slow, but that's okay. That's okay. It's better that you understand this than for me to rush through a whole bunch of slides. Okay. All right, so here is notation, which is, since I'm not going to go through much of the talk, it's not clear I need, but let me do this. Okay, so you have n underlying nominal states. You have some transition probabilities that are functions of action that define how the nominal state transition happens. there are some observation probabilities that say what is the observation you get when you're in some underlying true state. There's an initial belief state, which a belief state, this B notation, takes a history of observations and spits out a distribution over underlying nominal states. So that's what you're maintaining in a POMDP setting. Okay? So here's the point I want to make. Well, let me just make this point. Remember, our goal in a model was to make predictions of this sort. What's the probability of a future given history? So in a POMDP setting, the prediction of a future given history is just take the belief state for that history and multiply it out by a sequence of matrices that correspond to the actions and observations in that test. So remember, the test T is A1, oh, this should be superscripts. Somehow the superscript went away. It should be A super 1, A super 1, O super 1, A super K, and so on. So just, here it is. So you have the sequence of actions and observations. Just multiply by the corresponding transition probabilities for that action, observation, action, observation. So it's a vector times a sequence of matrices times this one length, this vector of ones, and that gives you the prediction. So the main thing I want you to get is that the following really nice thing about POMDPs, which is going to be preserved in PSRs, is that the prediction of a future given history is a linear function of the belief state. So it's the belief state times a matrix. The matrix is just the product of all these matrices. So what do I want to say? I want to make one simple point. The prediction of a test of future given history is a linear function of belief state. There's a matrix that you multiply by belief state, and that will give you the prediction. What is that matrix? That matrix is this multiplication of transition matrices and observation matrices. Okay, so why did I do all this? Here's where I'm going. So I'm now about to prove the result that I want to claim. That every POMDP with n nominal states can have rank no more than n. System dynamics matrix can have rank no more than n. I'm about to show that. Okay, so this is a system dynamics matrix. I'm going to replace all the histories. So remember, for every history, I can make predictions like this, right? There's a belief state according to the history, and then I multiply it by the corresponding matrix. Belief state corresponding to the history, multiply the corresponding matrix. Okay, so notice what's a belief state. A belief state is a probability vector of underlying nominal states. It's an n-dimensional probability vector. Now let's conceptually just imagine belief states in which all your probabilities are in state 1. A second belief state which all your probabilities are in state 2. So if there are nine nominal states, imagine the belief state which you know you're in state 9. A separate belief state which you know you're in state 8, and so on. So every belief state is now a linear combination of these 9 belief states. And so, pick out the histories that correspond to those unit basis belief states. Pick a history in which the belief state is you're in state 9. Pick a history in which the belief state is you're in state 8. So there are 9 such histories. So all the other rows will be linear combinations of those 9 histories. Because everything is linear. Because everything is linear, all the other rows will be linear combination of those 9 rows. What linear combination? Precisely, if you give me a belief state in which you spread out some probability over these 9 states, it'll be exactly those numbers that will multiply the rows to make a prediction for that belief state history, for that history. Just that. So that's a proof. That's a proof, by hand wavy proof, right? That the maximum dimension of the system dynamics matrix for an n nominal state POMDP is at most n. Which means what? Which means that with a rank n, dynamical system, we can remember things arbitrarily far back in the past because that's what PalmDBs can do. And we know there exist end state, nominal state PalmDBs that are much, that are arbitrarily more powerful than an nth order Markov process. So hence it proves that these are much more, that rank n dynamical system will be quite a bit more powerful than nth order Markov processes. Okay. So all this time, and all I've shown you is that this matrix can be thought of, and that from this matrix you can prove things like ranks of nth order Markov processes, models, and PalmDBs. Okay. So now let me at least finish. At least I'll get to some things. Okay. Let me get to this part. So now I'm going to show you a different model, which we call predictive state representation model. So remember that if it's a rank n system, there are n linearly independent columns. They're not unique, but let's imagine that these are the columns, and that let's remember those are core tests, all that I went through. So now the claim is what replaces the belief state is the predictions for the core tests. So what replaces the belief states in a PalmDB are predictions for the core tests. We talked about a little bit of this already. We noted that these n numbers, the predictions of the core tests, are a sufficient statistic of history, just like the belief state, history of observations, right? Just like a belief state is in a PalmDB. So that part is clear. What I'm about to show you is that there is a very particular parameterization which will generate this whole system dynamics matrix. So we talked about the fact that the prediction for a test T is a particular linear combination. Okay, you're all that. So now what I'm about to show you, and this is the missing piece to build a model, is suppose you knew these n numbers for a history H. And then I take action A and I get observation O. So now my history is one step extended. Right? I had my representation of state in this history. I took action A, I saw observation O, and now what do I need to do? All I really need to do is figure out how to compute this, and then I'm done. I've maintained state. I've maintained a sufficient statistic. If I can do that, then I've maintained an ability to keep a sufficient statistic. Okay, so that's the question. The question is, given this, how do I, and given this and the fact that I took action A and observed O, how do I maintain this? Okay, so here's the answer. So the prediction of the core test Q sub I, remember the tests were Q sub 1 to Q sub n. So the updated prediction of Q sub I, given extended history H sub O, HAO, is just by conditional probability rules, just this ratio. The prediction of a one-step extended future, extended by AO to begin with, in that history, divided by the probability, the prediction of just this one length future divided by this, given this history. So I want you to look at this for a minute, and if you get this, then I think you've gotten most of what I've been talking about at this point. So the ultimate result is to predict, to update my state, all I need is to do two inner products and take the ratio. What is this inner product? The numerator is is the prediction from my old history, which I knew, right? I knew the sufficient statistic for the old history. Is the prediction of the one-step extended future, right? QI is just some future, a specific future. So I sort of begin with AO and then I go to QI, and then divided by the probability of just the future AO. That's it. So now I can maintain my model. So what are the parameters of this model? The parameters of the model are these vectors, the M vectors. How many M vectors do I need? I need one for every action and one for every observation. And that's it. I need one for every action observation and core test, and one for every action observation. This is what I need for the numerator. This is what I need for the denominator. Okay. So now I can maintain my state and I can continue making predictions. So these are my model parameters. I just walked through this. And so every dynamical system of rank linear dimension n is equivalent to the model I just described, which is called a PSR model, is equivalent to a linear PSR with n core tests. Okay, I don't know what I'm doing here. Oh, this is meant to give some intuition. Okay, one thing that to keep in mind, one difference between POM-DPs and PSRs is when you think about rank of a matrix, when you think about computing a column that's linearly dependent on the n core columns, the linearly independent columns, the weights can be negative, right? When you think of a rank of a matrix, the weights can be negative. And that's unlike so the parameters can have negative numbers in them, unlike a POM-DP model, in which the transition probabilities are the parameters and the observation probabilities are the parameters, and they only have positive numbers in them. In fact, they're stochastic matrices. This has an implication. This has actually a major implication. One of the major implications is that there exist PSRs that can rank n dynamical systems that cannot be modeled by any finite POM-DP. So here's a way to say it. PSRs are, in a representation language, strictly more powerful than POM-DPs because there's negative numbers aspect to it. But I won't go into the math of that. Okay, so I've done a whole bunch of fairly abstract stuff. Let me talk about this. Let me talk about algorithms for a minute. Okay, so what did I show you? I showed you a representation of a model which is more powerful than nth order Markov models, more powerful than POM-DPs. But here's the thing that I forgot to emphasize, that I should emphasize. In a POM-DP, how do you learn a POM-DP model from experience, which I haven't talked about, of course. When I gave you an explanation of POM-DPs, I gave you an explanation which I assumed you know the map. You know what the observations will be from every state. If you don't, if all you're doing is experiencing the world and you're getting these observations, if all you're getting is a stream of observations and you're going to build a POM-DP model, because that's our goal, right? Our goal is to model the world from observations. Then you have to posit these hidden states. You have to posit the notion that, oh, there might be some latent states, hidden states, nominal states that I can't see, and it requires what's called expectation maximization to learn these things. So now, how many of you know what EM, or expectation maximization, is? Okay, good. So at least some of you know what that is. So, so the difference between doing EM to learn a POM-DP and to learn a PSR model, which I'm about to get to, is based on the following observation. Notice the representation of state in a PSR was simply predictions about specific futures, the core tests. Which means that the representation of state is just a bunch of predictions. So it's very different from representation of state in a POM-DP. There's no positing of latent variables, no positing of latent states, no need to do EM to learn. I'll show you how to learn these models in a minute, right? So there's no need to do any of the expectation maximization like things you have to do in a POM-DP. So how do we learn these models? So the advantage we have is the representation of state is in fully observable terms. So it will turn out that building a model is a linear regression problem. So no need for POM-DPs, no need for EM. You can learn a model that's equivalently expressive, or in fact more expressive than POM-DPs, but for our purposes at least equivalently expressive, and you can do it through linear regression. So that's what I'm about to show you. So there are two problems in learning a PSR model. First is to determine what the core tests are. And then once let's call that the discovery problem. And then given the core test to determine the update parameters, the M parameters. Okay, so let me show you how to do this. Get this out. Okay, suppose for a minute you knew the core tests. If you know the core tests, then I can set up a linear regression problem that solves for the parameters, the learning problem. It's very straightforward, really. Remember, there was a matrix multiplying the state representation that gives you the prediction of a one-step extended future. So all I have to do is from the data, compute the predictions of the core tests, estimate the predictions of the core tests from this history. Suppose I can generate history over and over again. Give me that for a minute. Suppose I can generate history H sub 1 over and over again. If I can generate it over and over again, then I can compute the probability of particular futures, the n futures in Q. So I can get these numbers, right? This is the probability of the Q sub 1 given H1, Q sub 2 given H1, Q sub 3 given H1 to Q sub n given H1. So that's my PSR state in history H1. I can estimate this from data. I can also estimate the probability of AO followed by Q sub 1, AO followed by Q sub 2, AO followed by Q sub n in history H1. That'll be this column. And this is a matrix that, when multiplied by this vector, produces that vector. So I can do this for a number of different histories. They have to be linearly independent, will have to give me a full rank thing, but if it's a core test, they will. And then I just have to solve for this matrix given these two matrices, which I can estimate from data. So it's a linear regression problem. Yes?
And this matrix, unlike the other one, is not infinite.
And this matrix is not infinite, yes. This particular matrix is not infinite. It's just the parameters that we talked about in the state update equation. So this matrix is not infinite, this matrix is not infinite. I can estimate, these are literally predictions of the future from specific histories, which I can just get from data. Literally just predictions of futures from histories I can get from data, and I just have a linear regression problem now to solve for these parameters. So no hidden states, no notions of hidden states, none of that. I can just take the data, get these numbers, and solve this by linear regression. So you get this big benefit, potential benefit, that you don't have to do any EM, just do linear regression to solve for the parameters of a PSR model. What I haven't showed you, of course, just assumed you knew the core tests. So I'll get to that in the next remaining 10 minutes. But I'm going to do spectral learning for that. So I'm just going to switch slides in a minute, but I want to at least show you the spectral learning idea, which is a slight variation of this. Yes?
Why do you need n histories?
Because, why do I need n histories? Because I want to make it an invertible problem. Right? Remember, these are if the rank is n, then these are n-dimensional vectors. So I have to compute this matrix. So I want n different histories so that I can make a invertible problem. Right? To solve for this matrix, I have to invert a matrix, right? I have to multiply by the inverse of this matrix on both sides. Any other questions about this? Yes.
Maybe I missed it, but why are we only getting one?
Oh, right, I don't. I have to do this for every AO.
No, but why not two steps into the future? AO.
Oh, because
A prime, O prime?
remember, in my modeling, all I really needed ever, one more, I think. Nope. There. All I really needed was this. Remember, to maintain my state, I just have to, if I have the state at a particular history H, if I have this quantity, the state at history H, I want to maintain it when I take an action and see an observation. And for that, all I needed was length one-step extensions. Now, what you might be thinking is, what if I want to predict more than one step ahead? And that I didn't show you an equation, but basically it's just like in a belief state, you have to multiply matrices out for corresponding to the actions and observations. Same thing. These are enough to make a prediction for any possible future. Just if you give me a sequence of actions and observations, I pick up the corresponding matrices or vectors, if you like, which you can combine into a matrix form for that sequence of actions and observations. And just multiplication of that, I should have put that slide, would make a prediction of the future. So what I'm showing you is how to find the parameters of the model from which you can predict any future from any history. Okay, so I wanted to show you the let me do this. Okay, I was going to show you, I had a whole 2 more sets of slides, but I'm not going to show you all of that. Let me get you the idea. So this is to look familiar. There's a time right now, there's a past, there's a future. This is the belief state representation I just talked to you about. I want to get you to the PalmDP idea, the spectral learning idea. Okay. I just talked about the fact that EM is, well, I didn't talk about the fact, but the reason why you want to avoid doing PalmDPs, if you can, is because EM is slow and has no guarantees and so on. And the PSR-based approaches are linear regression-based approaches, so they're fast. It turns out that they're globally consistent or consistent with the limit, that kind of stuff. Okay, so where do I want to go? Now I want to show you a slightly different idea that's connected to PSRs. It's called spectral learning, and it solves the discovery and learning problem in one go. And here's how it works. Suppose you have a data set. So here the data set is weather-related data, so maybe it's sunny or cloudy, and it's sunny, and it's sunny, and it's rainy, and so on. What does this mean? Snow, right. You can't see the snow symbol. Okay, I should know this from Michigan. Okay, so you've got a set of data like this, and so just like in the PSR stuff we just talked about, you can build these matrices. These matrices are just, I need a pen. Back. This pen. I want to leave you with one more idea before I finish this. So I'm going to use this. So P21 is a matrix in which all possible observations, and the entry, ijth entry, Pij, is the joint probability. Instead of conditional probability, joint probabilities. Not very different. The joint probability that the observation at the second time step was I, and the first time step was J. So O2 is I, and O1 is, O2 is I, and O sub 1 is J. So this is just things you can directly get from the data. Just like what we had before, right? Just length 1, history is length 1 tests. Think of it that way. But except instead of doing conditional probabilities, they're doing joint probabilities. There's a reason why it's slightly better to do that. And P1 is just the vector corresponding to the first observation. It's a vector. And P3x1 is the one-step extended idea. So look at every observation and think of this as a one-step extended history followed by a third observation. So first observation, second observation, third observation. So you get a vector, a matrix with how many matrices? As many matrices as there are observations. Okay, so this is very much like the PSR story. It is just statistics from the data of short-term histories, short-term futures. Okay, so what do you do with this? So here's the idea. Not this. Oh, this is what it's saying. Here's the idea I want to show you. if you build a portion of a system dynamics matrix, think of extending this by a dashed line. Think of extending the upper line by the upper horizontal line by a dashed line. And so this is the a corner of the system dynamics matrix, except again not with conditional properties, with joint properties, but it's not very different. If this matrix is full rank, that is, has the rank of the entire system dynamics matrix, then the following procedure works beautifully. You just do what's called the SVD, singular value decomposition of this matrix. How many of you know what a singular value decomposition is? All of you. All of you. Very good. Very good. Better than our students would have back in Michigan. Okay, so this is just a singular value decomposition. So the sigma is the diagonal matrix of singular values. These are left singular vectors. These are the right ones. So this matrix U, there'll always be such a singular value decomposition. The question is, what is the dimensions of U and V? There'll always be such a thing. Okay. So U could be in general n by m if the rank is m, if the rank is little m. So this is an n by m matrix, but the rank of it could be little m, and then U would be a n by m matrix. Everybody remember that from singular value decomposition? Okay. So hence the name spectral learning, because of course these singular values are a spectra of the algorithm. Okay. So what do we do with this? Here it is, in one slide, though it's very quick for you, I'm sure. Remember those matrices we were talking about with M's? They like to call it B's, which is fine. And the matrix looks like this. So all the parameters that we needed for a PSR model are being computed here with essentially the U matrices. All we need from the singular value decomposition is the U part, and then you can define a matrix for every observation which looks like this. I'm not going to go into the details of this because we don't have enough time. But I just wanted to communicate to you that the beautiful, simple idea I told you about PSRs with core tests can be done through singular value decomposition. With this matrix, with the left singular values, singular eigenvectors of the singular value decomposition, and gives you a closed form expression for which contains only observable quantities. Notice these are just statistics from data. This is just length 1 histories, length 1 tests. This is length 1 histories. This X is the same observation. So if you're learning a matrix for observation O, this will be that little o, and then one step future. And very simple linear algebra is basically solving the linear regression problem through SVDs. You can think of it that way. This is solving the linear regression problem through an SVD-like process rather than this linearly independent columns-like process that I did before. Okay, so I'm almost out of time. So let me just try to wrap up. So I went way slow, but that's okay. So there's a world of models out there called spectral learning models that build on PSRs, relate to PSRs, that would be more accurate. And the idea is very straightforward. You take data, you build a observable statistics matrix, which are basically matrices that contain short-term histories and short-term futures. So a portion of the system dynamics matrix. Then you do SVD analysis of the system dynamics matrix, and you've got a model. Without any EM, without doing latent variable representations, without doing any hidden states, without nominal states. And it's just as expressive, in fact more expressive, than these latent variable models. Now, in the remaining 2 minutes, I'm going to try and say what are the caveats. Now, for this thing to work perfectly, the the matrix you construct from data, this sort of solid matrix, has to have the rank you need, has to have true rank, has to have the rank of the linear dynamical system, has to have the rank of the dynamical system. And that's going to be impossible, because any true dynamical system, any real world system is going to have a huge rank. Think of weather, for example, or language, or English language, for example, or your language, right? It'll have a huge rank. So the assumption that you're doing singular value decomposition of a matrix of the true rank of the system is never going to be met. So the slides I didn't get to present to you is work from my postdoc and me, a student, which would have showed you how to deal with that. So I want to leave you with the message that there's a lot of work going on right now. Spectral learning is hot in a academic sense of hot. There's a lot of work going on and trying to deal with the fact that you don't have enough data. You don't have enough data to build a very large part of the matrix, and you certainly can't do enough to get close to full rank, true rank of the system. And so to build a theory of approximations when you don't have a complete rank, a perfect rank, how do you deal with that? That's what we've been working on. And there's a lot of very exciting work going on in that space. So this is a long trip to give you a small thing, but I hope you got something out of it. I'm happy to take questions. That's the American thing to do. Now we'll have questions. We can stop recording. And what's the score? Sorry.
So,
yes.
what could be the good metric for prediction in case of a spectral learning?
Good metric for prediction?
Yeah.
So if you started with a full rank, a part of the submatrix that had complete rank, this would give you a perfect. If you estimated the parameters so that the rank of the estimated submatrix is its true rank, and in the limit of data you've got perfect numbers in there, then this would be a perfect model. It'll give you perfect predictions, right? So the question is, when you can't do that, because you can't do that, you don't have infinite data, and you will never be at full rank. So then the question is, what happens then? And that's the question that, in fact, the rest of this slides are about. And the short answer is, there was a hope that if the stuff that you're throwing on the floor, so to speak, have very small singular values, then you're not throwing away much in terms of predictive power. Right? When you do SVD, you get singular values. Singular values can be ordered by size. If the rank you're throwing away, in effect, has very small singular values, the hope was that you would be not losing much prediction power. So what the first result I would have shown you if I got through these slides would be first a negative result, which is that that's not true, not without making further assumptions. That you can throw away very small singular values and still lose a lot of arbitrary amount of prediction power. But there are ways to fix it, and then that would be the positive result. Under certain other assumptions, conditions, you can recover. You can recover the result that if you're throwing away small singular values, you're not losing much predictive power. So that's the hope. The hope is that, yes, the rank, true rank is huge, right? The rank of the English, when you hear somebody speak, as an uncontrolled dynamical system, the rank of that will be huge. But that a lot of the numbers are very, very tiny, and that you can build a smaller system this way and retain prediction power. In fact, we're doing experiments on character prediction in Wikipedia text, and we're finding that in fact that's true. You can make pretty good predictions. But you may have been asking a deeper question. I'm not sure. Ask it again if you like.
So I'm asking for, we are using linear regression to predict something. And in case of, I will take a particular example. In case of social network analysis, in most of the graphs we find that eigenvectors are like almost constant. So learning spectrum is the like eigenvalues. So if we predict the eigenvalues, like metric, like suppose that we use AUC and all, it totally depends on the eigenvectors. So it's since it does not changes much, so it like we get no differences in terms of temporal predictions.
Okay, so the hope that if you throw away small singular values, you're doing okay, comes from the following simple mathematical fact. If you want to take an arbitrary matrix and you want to build a approximation to that matrix, which has low Frobenius norm error, what does that mean? That means, well, I hate having to say math in trying to explain something. There's some measure of difference called Frobenius norm difference. It turns out that if that's the norm you care about, then the way to construct the approximation is through the singular value decomposition. And furthermore, if you build it with a reduced rank, that the amount you lose in the reconstruction in this norm is the size of is the sum of the singular value squared, I think, that you throw away. So that result is the motivation behind the spectral learning sort of idea that minimizing the Frobenius norm is actually not a bad thing to do. But the reason why I'm saying this in response to your question is that, you know, the spectral learning approach is solving an implicit optimization problem, minimizing Frobenius rank. There could be other optimization problems that you could solve that would lead to better solutions. So here's one thing we're doing, actually right now, is we learn a model through the spectral learning, or PSRs, which is basically a kind of Frobenius norm minimization kind of thing. And then we just say, okay, we're going to now treat these as parameters, almost like a recurrent neural net, and do gradient descent to improve those parameters for an optimization norm we truly care about. For example, likelihood of future. So you can think of the path we're taking right now to sort of address your question is to say, all right, this is a very fast way to get an initial model. And then we can use it. The beautiful thing about spectral learning is very fast. That's the thing. It's just matrix, it's just SVD. So it's much faster than any kind of iterative EM-like approaches. So we initialize the model, and then we just treat them as parameters and do gradient procedures to optimize some other optimization measure we may care about. Whatever other optimization procedure we can do gradient descent for. So that's the kind of thing we're doing right now. And I didn't get to any of this stuff because it's so slow. Yes.
Thank you, sir.
Any other questions? Good.
So, yesterday, the day before, I spoke. So the other day, everyone's heard about when I spoke about options and temporally abstract predictions. And I think we should relate that. It's a bit different.
Yes.
But this is an important. Everything I talked about assumed we had state.
Yeah. So okay, good. Let me try to pick up on that thread. So a lot of this is about not knowing state and trying to form state and trying to build models purely from observations that are not directly giving you state, which is what the real world tends to be like. Now, by the way, how do people deal with that in reinforcement learning applications, right? The way people deal with it is when they don't have state, they have observations, they just make up, and it's not a bad way to do it, is they make up features of history, right? They may say, okay, if I just remember some specific things from the past, or I compute some features of history, then I'll at least get some approximate state, even if I can't prove it's fully state, you know, and it tends to work. I mean, people are very clever. Human ingenuity is quite strong, and so if you care about a domain, you know enough about the domain, that's how people usually handle partial observability. Just want to be clear about that. So then you just sort of assume your features are state, and you just run with that. That's one way to deal with it. But Rich wanted me to connect to options. So when Rich and I and Michael Littman were thinking about this PSR-related stuff, you know, one of the there were two motivating, if I recall correctly, there were two motivating ideas. One was, you know, we had options. We heard about options. Options have models. Option models predict the consequences of taking that option. You know, what state would you be and how much reward you'll get along the way. So those are predictions of futures, action conditional predictions. If you behave in a certain way, where will you terminate? How much reward you'll see? So that's not very different from what PSR state is like. It's predictions of specific ways of behaving. So our original motivation was to hope that there would be a set of options whose predictions would be state. That's one. If my memory serves me right, Rich, this is what you and I and Michael were thinking about, at least in part. The other, by the way, which is a really interesting line of work, is what's called successor state representations by Peter Dayan. It's a really clever idea. And if you want me to explain it, I'll explain it in a few minutes. But so we were trying to combine these two ideas of options and sort of representations of state that have the future in them into one through these spectral learning and PSR-like ideas.
So
Do you want to add something to it?
You have tests.
Yes.
The test is like an option.
Tests like an option. If you behave in this particular, the way I used it was open loop sequence of actions, but you can imagine a more closed loop policy as well.
So in principle, we could have an extension of PSRs where the tests, where we had option
Tests.
predictions.
Yes, option predictions. So
Maybe a general value function actually might be the way to think
you
about
could think of it as generalized value function. So we've done, yeah. So that's also a body of work. Yeah. So let me say it this way. What I've been trying to communicate to you is theoretically is hewing very close to theory, where we can prove things like if you do this approach, it's going to capture a sufficient statistic of history and so on. But the general idea is much simpler to state, which is a way of capturing state that could be useful for lots of different reasons would be to just make lots of predictions about the future of many different options, many different ways of behaving. And so one view to building an intelligent agent would be that you just make a whole bunch of predictions and maintain those predictions. And those predictions are your representation of state, but also those predictions could be useful for planning purposes and so on. So that's another view of this. I don't know, Rich, did you talk about this? Okay, so it connects to that. If Rich talked about that, then there's a connection here. What I tried to show you was a much more mathematically simple, but where you can say things about predictions and using predictions as representations of state. So the one idea that's common in the piece that Rich is referring to and that what I'm talking about here is the idea of using predictions of the future as representations of state. Predictions of what is one interesting question. We talked about predictions of very specific tests. We talked about predictions of tests derived through singular value decomposition. If you like, you can also think about predictions of options. You can think about predictions of other ways of describing future behavior. So that's the basic idea. Predictions about the future can be a good representation of your current state and could be useful for planning purposes. So that's the dual win that's the scope for. It turns things around on its head, right? To say predictions of the future are representation of current state is kind of perhaps a novel insight. Is a novel insight. Because you think of predictions of the future as useful for planning. You don't necessarily think of it as representations of state. Is the predictions of the future as representation of state? That's the novel idea here. Yes.
And, what would you say about POM-DPs? In that, what would be the representation of state?
So POM-DPs posit latent variables as an underlying structure that you don't observe as and maintain a belief state over a latent structure as a representation of state there, right? So belief states and predictive states are the counterparts. Belief states, so what's the difference? Well, I mean, one consequential difference is linear regression to do states versus EM. right? That's one consequential difference. So purely observable, you can get from purely observable quantities. Look, there are many cases where latent variables are the quantities of interest. That is, you're doing science and not engineering, right? And you're trying to discover latent states because that's what you want to communicate in some scientific enterprise, right? So it's not that they're trying to build a model. Often HMMs and POMDBs are useful, are primarily useful because of the latent states themselves. The scientist is interested in the latent states, as opposed to trying to just build a good model that the agent could use. It's the scientist's interest that often drives the interest in the latent state. So if you're doing that kind of science where you're interested in possible underlying latent states of the world, then you have to go there. Then it's a different problem, the problem we're interested in. We're interested in building knowledge that's useful for the agent, not for the scientist. I'm probably butchering how people would view POMDBs and HMMs, but this is my view of why do people use latent state models. It's because the scientist is interested in them. It's not clear that the agent cares in any way. Any other questions?